don't feel bad. I had to explain the joke to a couple people last hour. The dog bowl one. Yeah.
Still don't get it. Oh no. Lord.
You really don't?
Not really.
Dog bowl? I've never seen her bowl. Right? Lars, come on. All right. So we talked about energy of motion. We're going to talk about energy of position. Right? The ability to do work. Okay? Position is the ability to do work. If it falls or moves, it's going to do work. The two things we're going to talk about are gravitational and elastic. Gravitational is the ability for an object to fall and do work, right? So that's going to be related to height. So GP equals mgh. Mass times gravity, which is better known as what? Weight. Mass times gravity times height, mgh. Right? The higher an object is, the more work it can do when it falls, right? Yes, sir. Gravity is always going to be G. Yep. If we're doing a lab, it's 9.8. If we're not, it's 10. Sound good? Still joules, man. Still joules. All right. And then there's also elastic potential energy, which is right. Elastic potential energy, which is energy stored in a spring or an elastic material. Right? It can be a stretched spring. It can be a compressed spring. Okay? So, the energy contained in a spring is related to what? How much energy is in that rubber band that he just missed me with? What the energy in this thing is related to what? How far I stretch it. Right? Okay, and how stretchy it is. If this is a big, thick rubber band or a little tiny rubber band, right? So the K is how stretchy it is. If it's a spring, right? You can buy springs with different constants. Anybody who's ever had to buy springs? Any roboticists in here? Right? They sell them by K values. Okay, bigger, heavier springs have a higher K value. Yes, sir. No, it's not because of the x squared, right? So the K value is how stiff the spring is. The x value is how far you stretched it or compressed it, and that is squared. The farther you stretch it, right, it's not a linear value. It's an x squared value. It's a curve. Right? The farther you stretch it, it doesn't increase linearly. It increases squared. EPE. Is that what you're talking about? Yep. Okay. It can be positive, can be negative, because a spring can not only be stretched, but also compressed. That's where the old rubber band kind of fails us, right? You can really only stretch it. But in a spring, you can compress springs or stretch springs. So, depending on how they're constructed. Right? There are springs that you can't really compress because they're already constructed to be touching, the coils are touching. But, huh? That's where the springs fails us, yes. Okay. So, simple enough so far? The three types of energy we're really going to be focusing on are kinetic, potential, and EPE. We will touch on a little rotational, but that's still kinetic. And then we're going to talk a little bit about heat. Now, where does heat come into everything we've been doing so far? Okay. Right, when there's work done, we're going to lose some to friction. Absolutely. But we're not chemists, right? We're not worried about heat of things burning or nuclear power, any of that crap. We're worried about motion, right? Well, guess what? Friction makes heat, doesn't it? Is friction a force?
Yep.
What happens if we take a force times the distance? We get work, right? So can friction do work? Yeah, friction can do work. Absolutely. Friction's a force acting over a distance. What happens though? It creates heat, right? So in our magic energy equation, right? In our magic energy equation, let's say we're talking about a roller coaster, right? Let's say you have a roller coaster that, and you're trying to figure out how much energy is right there, right? We do energy before equals energy after, right? In our grand energy equation, we're going to have some GPE here. At this point, we're going to have some GPE, some KE, and what? What do we have to take into account? Plus the work done by friction, right? So in our energy equation, GPU1 is going to equal all of these added together, right? So this is, I'm kind of getting ahead of myself, but this is where we're going with these problems. GPE1 equals GPE2 plus KE plus work done by friction. That's my equation. Now I just plug my crap in and solve. I would be asking for maybe what's the height of the second hill or something like that, right? And you're going to plug your crap in there and you're going to solve it. So we're kind of back to that same thing from last chapter. You're going to draw a picture. You're going to make your equation from the picture, and then you're going to plug crap into it. It's actually fairly, now that we beat you to death with last chapter, right? Most people traditionally have found this one to be the easiest chapter because it's the same basic concept. Draw the picture, right? Make your basic equation and plug crap into it. So that's pretty good. But just knowing that, what I was talking about, work done by friction is the force of friction times the distance that the friction acts. Right? So if I said you were going 80 miles an hour and you slammed on your brakes and you stopped over 100 meters, right? You could calculate, you'd have the KE from how fast you're going equals the work done by friction, right? Because friction stopped you, which would equal the force of friction times the distance, right? If you know the distance and you know the kinetic energy, you could find how much friction there is. So that's what we're doing with this, right? That's where we're going with all this stuff. Now, if you're going to go into engineering, you're going to see this equation. If you're not, don't worry about it. The thermal energy created equals the force of friction times the change in position, right? Which is the distance traveled. If you're not going into anything beyond that, don't worry about it. But you'll see this. This is a pretty common friction calculation. Right? They need to know how much friction there is when you're designing a roller coaster or anything like that. You don't want that roller coaster to get stuck between the hills, do you? So you need to know how much friction there is. Position. Change in position. Okay, so thermal energy is the amount of work done by friction. That's what we're going to be doing from thermal energy. There's obviously more types of thermal energy you deal with than that, but the one we're going to deal with is work done by friction. And the last one, power, is the rate at which work is done. Some of you guys are more powerful than others, depending on your grades, right? No, not that kind of work. You got to have movement to have work, right? Some of you guys don't do that much either. I'll be nice. We know that rate equations are always over time, right? Rate is always over time. So power is work over time, right? And if we use a little math magic, all right. Power is work over time, right? What's work equal to? What's work equal to? Yeah. Force. Power can also be force times velocity, right? If you've got a constantly moving object, right? If you're accelerating, that's different. That's calculus, man. But so it can also be that little math of magic there. So it's FD over T. Work is force times distance. Yeah, when you're multiplying, it doesn't matter what's divided. Okay, now our units of power are watts. Right? Watts. A joule per second is a watt, or a newton meter per second. Right? See how these? It's its own. Right? A watt. Watt is our base unit of power. Okay. Olden days, even newer days, but they had horsepower, which I don't know how they calculated. It had to be some average-sized horse, how much work an average horse could do in an hour or whatever. But 745.7 watts is a horsepower. Again, I don't know the origin of the horsepower exactly, but it has something to do with how much work a horse would do. Yep. Yep. So, yeah, a watt hour. Yeah, it kind of works backwards, right? A watt is power. Okay, a watt is power. A watt is joules per second. What happens if you took joules per second times essentially seconds time period, right? You get energy. So why watt hour? The reason for the watt hour is it gives you a better idea of how much, because we talk about power in watts, right? It gives you an idea of how long that battery is going to last because it's got the time in it, right? But in reality, it's just giving you energy. Does that make sense? So, all right. Questions? Any other questions? That's it. That's your basic notes. Obviously, there's more to it as we get going, but once, twice.